All right, chemistry. This is your video lecture for Chapter 6, Section 1 and 2. We're going to breaking this up into 3 parts, so we're going to tackle Section 1 first. Your objectives for this section: define chemical bond. That's one thing we want to keep in mind as we go through this entire chapter with regard to chemical bonding. We don't want to forget the basic foundation of what we're talking about. It can create an error in our scheme of understanding. Second, describe and differentiate between ionic, polar covalent, and nonpolar covalent bonding. There are 3 major types of bondings that we're going to cover. One of them is ionic, one of them is covalent. Here we're actually going to refer to 2 subcategories of covalent bonding: nonpolar covalent bonding and polar covalent bonding. Third objective, calculate and classify bonds according to electronegativity differences, which is very closely related to our 4th objective, which is calculate the percentage of ionic character of any bond using electronegativity differences. So what's going to happen is you're going to be given electronegativities, you're going to calculate the difference between them, and then based on whatever number, that result that you come up with, you're going to conclude certain things like what type of bond it is and then the percent ionic character. So let's get started. Let's start by defining chemical bond. It is a mutual electrical attraction between the nuclei and valence electrons of different atoms that bind the atoms together, right? And the nucleus of one atom, the valence electrons of another atom, and the electrostatic attraction between the two, right? Protons and electrons, that positively charged nucleus and then the negatively charged electrons in the electron cloud. That is the force that binds these things together. Now, there are a few different ways that this can actually take place, a few different ways that this can happen. But it's all happening as a result of these electrostatic attractions between the nuclei and valence electrons of different atoms. The different ways that we classify bonds have to do with the way that the valence electrons are distributed around the nuclei of combined atoms. So we're going to talk about the location of these electrons in space. So we're going to start by introducing our first type of bondings, ionic. We're not going to get too much into ionic bonding right now. We're just going to introduce it. We'll cover it more in Section 3. Ionic bonding is a chemical bond resulting from electrostatic attraction between cations and anions. So just like the name suggests, when you have ionic bonding, it's the bonding of ions. And so, for example, when you have elements like sodium that wants to give up 1 electron, and then chlorine that wants to gain 1 electron, you're going to end up with an atom giving away an electron. Well, that electron doesn't disappear into the ether. It goes somewhere. The reverse part of that is chlorine is a type of atom that wants to gain an electron. Where does it gain that electron from? Again, it doesn't just synthesize it out of thin air. It has to come from somewhere. In this example, the electron that chlorine gains is the exact same electron that sodium lost. And so there is a transfer of electrons from one atom to the other. And from Chapter 5, you should be able to fully understand that has sodium resulting in a positive 1 ion and chlorine becoming a chloride ion and negative 1 charge. And it is the electrostatic attraction between the positives and the negatives of those 2 ions that cause them to be very strongly attracted to one another. For example, we start with element A and element B. Element A loses an electron. That electron is completely transferred into element B, and it becomes a negatively charged ion. The electrostatic attraction, right, these opposite charges attract one another, and this is called an ionic bond. Moving on, we'll talk about a covalent bond. The covalent bond is a chemical bond resulting from the sharing of valence electrons between 2 atoms. Now, let's not skip past this word covalent. There's meaning in that word that can help us understand what it is. Covalent bond is the sharing of valence electrons. Covalent. Co as in cooperate, to operate together. So these are together. Valence electrons. This is a working together of valence electrons. The valence electrons of 2 different atoms. We want to remember the whole reason that atoms are going to bond is so that they can gain a full 8 valence electrons, satisfy the octet rule, gain a noble gas electron configuration, and be stable. Now, if 2 atoms can agree to share valence electrons with one another, they can both gain a full valence shell from that act of sharing. Now, they're both accessing those electrons, so they both are benefiting, but because they're both using the electrons, they're actually stuck together. That is a bond. Now there are two different types, two subcategories of covalent bonds. One is known as a nonpolar covalent bond, sometimes referred to as a pure or perfect covalent bond. And in a pure covalent bond, the electrons are shared equally between the two atoms that are bonded. Okay, those two electrons involved in the bond are going to be right smack dab in the middle between those two atoms. But most covalent bonds have electrons being shared unequally between atoms. We call this a polar covalent bond. This is what happens when one atom is much more electronegative than the other. Remember, electronegativity is the measure of an atom's ability to attract another electron. And so if one atom has a stronger ability to attract electrons, that electron is actually going to shift over and be closer to the more electronegative atom. As long as it doesn't result in the ionization of that atom, there's still a sharing, but it's unequal. You're sharing, but one of the atoms is having more access to the electrons in the bond than the other. They're both still sharing, but it's unequal. Now, looking at those ionic bonds and covalent bonds, there is no bond that is completely ionic, a true and perfect transfer of electrons. And a completely covalent bond is actually very rare. Okay? A pure, perfect, non-polar covalent bond is a little bit rare. It happens, but it's a little bit rare. We'll talk about that in a few slides. In nature, most bonds range somewhere between these two extremes of that pure ionic and pure covalence. Usually we're going to find real bonds somewhere in between there. And so we're going to see that the degree of the ionic or covalent character can be estimated by comparing the electronegativities of those atoms, the two atoms that are involved in the bond. And when you compare the electronegativities of those two atoms, when you find that the difference between the electronegativities is greater, you're going to find that that bond is more ionic. It has more ionic character. For example, once you calculate the difference between the electronegativities of two atoms and you find that that difference is somewhere between 1.71 and 4, we automatically consider that bond ionic. For example, let's look at a bond between cesium and fluorine. We're going to look at the periodic table that lists the electronegativity values, and if you're not sure where that is, it is actually on the next slide on your notes, so you have access to all of those values. So take a peek at that periodic table, find fluorine. You'll see that it has an electronegativity value of 4.0. It's the highest on the periodic table. And you can find cesium in the bottom left-hand side of the periodic table, and you'll see that it has an electronegativity value of 0.7. I do simple arithmetic, 4.0 minus 0.7, and I get 3.3. The fact that it's a 3.3 electronegativity difference puts it right in the middle of that 1.7 to 4.0 range. Because it's right in the middle of that range, I consider this an ionic bond just by looking at the electronegativity difference between the two atoms. So what can we conclude from this? Well, cesium is going to become a cation, and fluorine is going to become an anion. It's going to become a fluoride ion. So here are the values that you have to use, but are you saying that we are going to have to memorize all of these electronegativity values? No. This is the reason that I've printed this periodic table in your notes, so that when you go to write your quick write, you have access to this information while you execute your quick write. What about our quiz? This table is going to be printed on your quiz. You're going to have access to these numbers. These numbers are not something that you need to memorize. What you're learning in this section is how to use this information. Just like the periodic table is a table used for reference. You're not supposed to memorize everything in the periodic table. You're supposed to know how to use the information in the periodic table. So, when we're talking about ionic character and covalent character, we're going to see covalent bonds occur if the difference in electronegativity is less than 50%. So, let's look at some examples of covalent bonds. A bond between two identical atoms is completely covalent. That's that pure covalent bond that we talked about earlier. That's very rare. It does happen, but it is rare, and in fact, it only occurs between certain atoms. Now, this is a mnemonic that I have listed here, Brinkelhoff. This is a mnemonic that allows you to remember easily the 7 elements that form diatomic molecules. That means that if you find pure bromine, pure iodine, pure nitrogen, pure chlorine, pure hydrogen, pure oxygen, or pure fluorine in nature, it's not going to be a single atom of that element. It's going to be a diatomic molecule. Di meaning two, atomic meaning atoms, molecule. So it's a molecule that is made up of two atoms. So that's why you see oxygen, the oxygen that you breathe to stay alive, isn't just O. It's not just a single atom of oxygen. It's O2. When you see iodine or nitrogen, nitrogen gas that makes up 3/4 of Earth's atmosphere, it's not just a single atom of nitrogen. It's N2 because they're diatomic molecules. Now, if we find a molecule that's diatomic, it's two identical elements bonded together, I think you can see that they're going to have the exact same electronegativities because they're the exact same atom. And if they have the exact same electronegativities, the electronegativity difference is going to be 0. When the electronegativity difference is 0, you're going to fall into the category of a nonpolar covalent bond. I've referred to that already as a perfect covalent bond or a pure covalent bond. But it's a covalent bond in which the bonding electrons, the two electrons that are involved in the bond, are shared equally by bonded atoms with the resulting balanced distribution of electrical charge. That means between the two bonded atoms, right, between the two hydrogen atoms or between the two oxygen atoms or between the two fluorine atoms, the two electrons that are involved in the bond are exactly in the middle between those two atoms. They're not closer to one or the other. They're perfectly splitting the distance. Once we've concluded that we have a nonpolar covalent bond by calculating the electronegativity difference, we can conclude that this bond has somewhere between 0% and 5% ionic character. What numbers do you have to calculate for this electronegativity difference? If you do the calculation and your number comes, your electronegativity difference is between 0 and 0.3, that's how you know it's a nonpolar covalent bond. Then you know that the percent ionic character is somewhere between 0 and 5%. Talk about the other type of covalent bond, polar covalent bond. Polar simply referring to an unequal distribution of charge. And in this context, we're talking about where those charged particles are, right? The electrons. And if two electrons are involved in a bond, if they're unequally distributed, that means that they're simply going to be closer to one atom or the other. Okay, they're not going to be smack dab in the middle. A polar covalent bond is a bond where the united atoms have an unequal attraction for the shared electrons. So what we're going to see here is we're going to see we're not bonding identical atoms, right? Because if there are identical atoms, you're not going to have an unequal attraction. You're going to have an identical attraction. But your difference in electronegativity isn't going to be so great that it results in ionization. Okay, we're still going to have a covalent bond. It's just not going to be a perfect even distribution of charge. Those two electrons are still being shared by both atoms. They're just closer to one atom over the other. And so you will be able to conclude that you're looking at a polar covalent bond if when you calculate the electronegativity difference, you find a number somewhere in the range of 0.3 to 1.7. So if it's in that range, you can conclude that it's a polar covalent bond and that the percentage ionic character is somewhere between 5% and 50%. All right, let's look at some examples. If we're looking at a bond between hydrogen and hydrogen, we got to find the electronegativity. So look up that periodic table with the electronegativity values on it. You can find hydrogen in the top left. You see that hydrogen has an electronegativity value of 2.1. Let's find the difference between those two numbers. It's 0. Look at that. Surprise, surprise. So there's no electronegativity difference. It means that neither atom is pulling on those bonded electrons any stronger than the other one. This results in a non-polar covalent bond. But if we were to bond hydrogen to chlorine, okay, we find chlorine over on the right side of the periodic table a little bit closer to the top. We see that chlorine has an electronegativity value of 3.0. We find the difference between that 3.0 and hydrogen's 2.1. We end up with a difference of 0.9. Well, if you're looking through your notes and using your notes appropriately, you can conclude that an electronegativity difference of 0.9 results in a polar covalent bond. So what we're doing here, what we can say is, because chlorine is more electronegative in this hydrogen-chlorine bond, it has a stronger attraction for the electrons in the bond. Thus, an uneven, meaning a stronger pull on the electrons. Right? So those electrons are going to lean closer to chlorine. Now, they're still being shared. That's a really important detail. They're still being shared, but this just closer. They're located closer to the chlorine atom. Now, because the electrons are closer to the chlorine atom, we say that chlorine atom has a partial positive charge. It's not a whole positive charge because we haven't experienced ionization yet. These electrons are being accessed by both atoms in the bond, but we do say because the electrons are closer to one end or one pole of the molecule or compound, that there's a partial positive charge and a partial negative charge on that compound. The last type of bonding that we're going to introduce, we're not going to cover it in a lot of depth, we're going to leave this for section 4, is metallic bonding. And regardless of what state of phase you're looking at, when you have a whole bunch of metals around each other, when you have metals in general, metals want to give up their electrons. You see that they're on the left side of the periodic table and that they have somewhere between 1 and 3 valence electrons. That means the quickest way for them to get a noble gas electron configuration and that sort of stability is to donate their electrons. So they eject their electrons pretty darn readily. Well, if you only have metals around, you have nothing to accept those ejected electrons. And so you end up with a whole bunch of electrons just zooming around. Okay? They're not being accepted and held by anything. They're free to move. Free-moving electrons are called an electron sea, right? Like the ocean, electron sea. And it's this sea of electrons that results in all the typically metallic properties that you can think of. The luster, also known as the shine of metal, malleability, ductility, and the ability for metal to bend but not shatter or be broken. And then the electroconductivity, or metal's ability to conduct heat, all results from that electron sea, which we'll cover in more detail in Chapter 4, but we're just introducing it here. You guys want to know a quick trick to keep track of covalent, ionic, and metallic bonds? Just look at what types of elements are combining. There are only 2 different types of elements that we're going to be considering right now. We have nonmetals, we have metals. Only 2 types. So look at the different combinations that you can have. You can have 2 nonmetals get together. And when you have 2 nonmetals get together, that's going to be a covalent bond. It might be a polar, it might be a nonpolar, but it's going to be some sort of covalent bond when you have 2 nonmetals together. You can have 2 metals. When you have 2 metals together, that's going to be a metallic bond. That one's a little bit easier to understand. And then when you have 1 metal and 1 nonmetal, okay, one of each, that's an ionic bond. So that's a quick trick in order to remember that sort of stuff without being too stressed out. Now I have a whole bunch of examples for you guys to take down. You don't have to take down all 10. You can practice if you want to a little bit. But get down maybe 3 or 4 of these, and that's really all you need to have, because if you can do it just a few times, you can do it forever. So determine the electronegativity difference, the bond type, and identify the more electronegative element with respect to the following atoms. So we have 10 examples here. And here are your answers, and I'll talk through a couple. Number 1, hydrogen and fluorine. Look at the periodic table with the electronegativity values on it. Again, don't memorize this, just look it up. Okay, use it as a reference table. Fluorine has a value of 4.0. Hydrogen has a value of 2.1. I calculate the difference. The difference is 1.9. That makes the bond type ionic. And in this situation, the more electronegative element is fluorine. So fluorine is going to be the anion there. Looking at 2, bromine and bromine. We'll look at the periodic table with the electronegativity values. Bromine has the electronegativity value of 2.8. And if I have bromine bonding with bromine, I'm looking at an electronegativity difference of 2.8 minus 2.8. It's 0. That's a pure covalent bond. It's a perfect non-polar covalent bond because they have the exact same electronegativity. Looking at aluminum and sulfur, look at the periodic table with electronegativity values. I see that sulfur has a value of 2.5. I see that aluminum has a value of 1.5. See the difference is 1, right? 1.0. That makes the bond type a polar covalent. And the more electronegative atom is sulfur. All right, guys, that's going to sum up our first part of our 3-part video lecture. This has been the introduction to chemical bonding. I will see you next period.